Just go to the hospital. Say, hey, can I borrow this for like a minute?
I got in trouble at the hospital after surgery because I was trying to.
I got in trouble at the hospital never.
So, the next several chapters are going to be dealing with derivatives. So we're going to learn about what derivatives are and what they can be used for. So again, almost all the chapters except the very last one is going to be dealing with derivatives, right? The last chapter deals with the opposite of derivative. It's called an antiderivative. So we'll learn about that and what we can use that for. But like I said, most of the course from here on out now is going to deal with derivatives, and we're going to see a fairly close connection to what we learned about limits once we get into what a derivative is and what it's used for. But first, we'll do a bit of review about non-permissive values. When the domain of a function is not given, it's assumed to be the set of all real values of x for which the given function is defined, or when it exists, when it's real. For example, a function not defined would be when we have a denominator of 0 or a negative number under an even root. So we're asked to state the domain of the following, which is another way of asking, what are the non-permissive values? And in the case of a linear function like the first one, there are no restrictions on x. Okay, so we can say that the domain here, and we can write it, and I guess I don't have to write domain because that's what the question is asking, but we can write it using interval notation. Remember, with interval notation, you're always going to have two numbers, the smallest value followed by the larger value. They're separated by a comma, and the shape of the brackets is important. If the brackets are square, it means that that n value is included, but you can never include infinity because you can't put a value to it. So they're always rounded brackets. Same thing with question 2. This would be a fourth degree polynomial. There's no restrictions on x. The only time you're going to have restrictions on x is when you have a denominator involving x, or maybe the radicand involving x. So the radicand is the expression under the radical. So once again, the domain here would be all real numbers, so we can also express this using set notation, all values of x such that x is an element of reals. That's another way of saying all values, positive, negative, fraction, decimal, etc. For number 3, though, we've got a denominator here involving x. Because the denominator is 2x, we could say that 2x can't equal 0. You cannot divide by 0. And if you divide both sides by 2, then you'd say that x can't equal 0. 0 divided by 2 is still 0. So here we would say the domain would be all values of x such that x cannot equal 0, but otherwise all other real numbers. Question 4, again, you've got a denominator involving x. X minus 1 cannot equal 0, so x cannot equal 1. So you can write that in set notation like I just did for number 3, or we can still use interval notation. If x can't equal 1, that means that x can be from negative infinity to positive 1, neither are included, and also from positive 1 to positive infinity. Because you've got those rounded brackets, it means that 1 is not included. So you can use set notation like we did for question 3, or interval notation. When you have the radicand, which is the expression under the radical involving x, you cannot take the root of a negative number, so the radicand has to be greater than or equal to 0, which means x has to be greater than or equal to 2. So if we use set notation here, we would say the domain would be from 2 to positive infinity. And note the square bracket on the 2, because x can equal 2. You can take the root of 0. You just can't take the root of a negative number. Right, same thing with question 6. Can't take the root of a negative, so the radicand 3 plus x must be greater than or equal to 0. And in this case, x has to be greater than or equal to negative 3. Remember, the rules for solving inequalities are the same as with equations. The only difference is if you multiply or divide then by a negative number, the inequality will reverse. We haven't done that. We've added or subtracted values to both sides, in this case subtracted. That doesn't change anything. Only if you multiply or divide by a negative does the inequality reverse. So if we write the domain here in interval notation, we would say from -3 to positive infinity. The -3 is included, the positive infinity is not. Number 7, we're back to a denominator, and the denominator cannot equal 0, so x squared plus 5x plus 4 cannot equal 0. And so we need to find out where it does equal 0, and we can do that by factoring. The factors here are x plus 1, x plus 4. So this expression will equal 0 when each factor equals 0. So x plus 1 cannot equal 0, so x cannot equal -1. And x plus 4 cannot equal 0, so x cannot equal -4. You could do the domain in interval notation. You'd have to have 3 different intervals, from -infinity to -4, from -4 to -1, and then -1 to positive infinity. Or we can use set notation by simply saying that x cannot equal -1 or -4, but otherwise all real numbers will work. So same thing with number 8. We've got a denominator. Denominator can't equal 0. And so in this case, we'd have to factor that polynomial to find out what values of x do make it equal to 0. And because this is third degree polynomial, we go back to our factor theorem. Okay. Now in 30-1, we would use our graphing calculator in order to find the first x-intercept, which would give us our first factor. But because you can't use graphing calculators in this course, you have to go and look at the constant term and talk about our potential integral zeros. They are factors of the constant term. They're at plus and minus 1, 2, 3, and 6. We talked about that in 30-1. These give you numbers to start checking to see which of these numbers, when you plug into that third degree polynomial, which of those numbers give us an answer of 0. Remember, the remainder theorem says that if p at a equals 0, that's saying that the remainder, when you divide the polynomial by x minus a, the remainder would be 0, which means that x minus a divides evenly into p at x. So therefore, x minus a is a factor of p at x. Okay? So if we want to know if -1 is a 0, that would mean that x plus 1 is a factor. And we would use synthetic division normally to divide. Remember, we change it from x plus 1 to x minus 1, which would allow us to add the terms as we go along using synthetic division. So we're going to divide x minus 1 into 1x cubed. There is no x squared term, so remember we have to include that with a coefficient of 0. Then the minus 7x, then the minus 6. And then we multiply and add. 1 times -1 is -1, and we add. -1 times -1 is +1, and we add. -1 times -6 is +6, and we add. The last number tells you the remainder when you do the division. Okay, Brighton? Because the remainder is 0, that means that x plus 1 divides evenly into the polynomial. It's a factor of the polynomial. But this also tells us what the other factor is, the quotient. The numbers at the bottom tell you the coefficients of the quotient. We now know that x plus 1 is a factor. The other factor will be the quadratic, because we divided a third degree by a first degree. That gives you degree 2. And that would be x squared minus 1x minus 6. And again, this cannot equal 0. And we can factor that quadratic. it'd be x minus 3, x plus 2. So we could set each factor and say it can't equal 0 and then solve for x, but I'm sure you can go straight to this next step, which just says x cannot equal -1, +3, or -2. Those are the three values that will give a denominator of 0. So if we're going to write our domain, I'd probably use set notation here, all values of x such that x cannot equal. And it doesn't really matter what order these are written in. You just have to state that you have those three restrictions. Okay. Now for number 9, we're back to a radical, but there's two things we have to look at. In this case, t squared minus 3 has to be positive, but it also cannot be 0, because if t squared minus 3 equals 0, then you've got a denominator of 0. So in this case here, we would say that t squared minus 3 has to be greater than 0, not equal to. And back in 20-1, you may have been taught how to solve this type of inequality, right? You can add the 3 to both sides, that's no problem, but when you take the square root of both sides, what does that do to the inequality? I think the best way to determine what the restrictions on t would be here would be to look at the graph of t squared minus 3. So that would be the same as the graph of x squared minus 3. It's the graph of x squared shifted down 3 units. So its vertex would be at -3. And it's going to open upwards because the coefficient in front of the t squared is positive. Remember that from 20-1, when a quadratic has a positive initial term coefficient, it opens up. When it's negative, that's like you have an a value of negative, a negative value for a. That reflects the graph over the x-axis. But this one has a positive a value, so it's going to open up. And the solutions to this inequality will be where this graph is above the x-axis. We want to know, where is t squared minus 3 greater than 0? That's another way of saying, where is y greater than 0? Where is this graph above the x-axis? So the key then to determining that is finding out where these x-intercepts are. That's what we need to do. Find out where these x-intercepts are. And we can do that by going back and solving where t squared minus 3 equals 0. That'll give us the x-intercepts. So this we can do by adding 3 to both sides. And remember, when you take the square root of both sides and you're solving an equation, there's always the positive and negative root, because there's two x-intercepts, one negative, one positive. And they're exactly at root 3. Now you can find out what that is as a decimal, approximately 1.7 something, but you don't need to. In fact, you want to use exact values. So this x-intercept here is at negative root 3, comma 0. This x-intercept is at positive root 3, comma 0. And remember that because t squared minus 3 has to be greater than 0, again, we're looking to see where is this graph above the x-axis. It is now above the x-axis from negative infinity to negative root 3, and then from positive root 3 to positive infinity. T cannot be any value greater than or equal to -3, less than or equal to +3. So there's our domain. Number 10, very similar. You've got a radicand that's a quadratic. Because you cannot take the root of a negative number as well, denominator can't be equal to 0. That means that m squared plus 2m minus 8 has to be greater than 0. Can't equal 0 because then you have a denominator of 0. So once again, we want to know what this graph looks like. It's a quadratic. It must be greater than 0. So we're looking to see where is this graph above the x-axis. And like in the last example, it's those x-intercepts that are really key. We can find the x-intercepts by factoring, find out where it does actually equal 0. So the factors here would be m plus 4, m minus 2. So the solutions would be at negative 4 and positive 2. Those are the solutions to the quadratic. They're also the roots. They're the zeros. They're the x-intercepts. So if we were to graph this one, we don't exactly know where the vertex is, but we don't need to know where the vertex is. We know it opens upwards because it's a positive m squared. We have x-intercepts of negative 4, positive 2. We know the y-intercept is at negative 8. The constant term tells you the y-intercept. We don't know exactly where the vertex is. We could find it, but we don't need it. Quadratic would look something like that. And again, like before, we are concerned with determining where is this graph above the x-axis. Because the radicand has to be greater than 0. It can't be negative, it can't be 0. It must be only positive. And a function is positive where it is above the x-axis. So in this case here, our domain would be from negative infinity to negative 4, and then from positive 2 to positive infinity. Would you agree with that, Brighton? Did I do okay? Okay, that's great. All right, number 11. So no denominator here. So 0 having a value of 0 isn't an issue, but we've got radicals. We've got two different radical expressions, two different radicands. And both of them have to be greater than or equal to 0. So that's where we'll start. We'll say that the first radicand of x has to be greater than 0. The second radicand of x plus 3 has to be greater than or equal to 0. Therefore, x had to be greater than or equal to negative 3. So these are two conflicting statements. Okay? So what we need to do is we need to choose the statement that satisfies them both, which would be that x is greater than or equal to 0. All numbers greater than or equal to 0 are also greater than or equal to negative 3. But all numbers greater than or equal to negative 3 are not also greater than or equal to 0, like negative 2. That's greater than or equal to negative 3, but not greater than or equal to 0. So you need to prove or choose the statement that satisfies them both. And if we're going to state the domain, once again, we've got two choices. We can either use interval notation or set notation. Interval notation is the easier one here. There's our domain. Right, question 12. Again, we've got two different radicands. The first one, t, has to be greater than or equal to 0. The second one, 8 minus t, also has to be greater than or equal to 0. And so for that second piece, I would add the t to both sides. So that doesn't change the inequality. That would only happen when you multiply or divide by a negative, and that's not what we're doing here. We're just simply adding t to both sides. So in this case here, you actually get two statements that don't conflict. You can put them together, and you can say that our domain would be all values of t such that t is greater than or equal to 0, as well as less than or equal to 8. So I'm going to use set notation for this one. Okay, so t is greater than or equal to 0, less than or equal to 8. And t is an element of real numbers. Now, number 13. You've got a radical within a radical. And remember, the restrictions we have on radicals is that the radicand cannot be negative. So there's a couple things that we need to look at here. We need to say that 2 minus x has to be greater than or equal to 0. As well, 3 minus the root of 2 minus x also has to be greater than or equal to 0. So the first one is fairly straightforward. I would just add the x to both sides, and now we can say x has to be less than or equal to 2. For the second one, I can solve this inequality again using the same rules that we use for solving equations. The only difference, once again, is that if you multiply or divide by a negative value, the inequality reverses. So probably what I would do here first is I would add the 2 root 2 minus x to both sides to make it a positive over on the other side. To get rid of the radical, we will square both sides. If you subtract 2 from both sides, you're going to have 7 greater than or equal to negative x. And now to find out what positive x is, we would divide both sides by negative 1. And now if you multiply or divide by a negative, the inequality reverses. So instead of having negative x less than or equal to 7, we would say x is greater than or equal to negative 7. And once again, these two statements can combine into one. Your answers are all values greater than or equal to negative 7, less than or equal to positive 2. So we would say that all values of x such that x is greater than or equal to negative 7, less than or equal to positive 2. So there's the domain for that function. Okay? Right, so you also learned about composition of functions. Before, this was something that you learned back in 10C. The composition of f and g can be written as FOG, defined by FOG at x or f at g at x. So that means that g is embedded into f. So we've got our two functions, f and g. The first one is FOG, which again means f at g at x. The order is important. Okay? The second letter G is going to be embedded into the first f. And so this is done by taking the function f, which is 2 minus 3x, and you're going to embed g into that, which means that wherever you see the variable in f, which is after the 3, you replace it with g. That's what that means. You're going to embed g into f. And then we simplify. Negative 3 times 5x squared is negative 15x squared, and negative 3 times x is negative 3x. So that'll give us negative 15x squared, take away 3x plus 2. Normally we write our polynomials in order of descending power, normally. The second one is GOF, or G at f at x. So it's the opposite. In this case, you're going to embed f into g. So wherever you see the variable in g, which there are two places where you see the variable in g, one after the 5, you're going to replace that with f and do the same thing that happened to the x, which in this case it's squared, plus for the second x, again you replace that with 2 minus 2x, or minus 3x I should say. I need to fix that. I wrote 2x in that first piece, so should have been 3x. So if we square that binomial, remember, you don't just simply square both terms. When you square something, it means multiplying it by itself. It's going to be 2 minus 3x times 2 minus 3x. There is a shortcut we can use for squaring a binomial, which is square the first term, multiply the two terms together, and double. 2 times negative 3x is negative 6x. Double gives you minus 12x. And you also square the last term. Negative 3x all squared will be positive 9x squared. And then we have the positive 2 minus 3x. So to finish this off, we got to multiply out the 5. And simplify. So I've got 45x squared, negative 60x, take away 3x is negative 63x, and 20 plus 2 is positive 22. So there's the value of GOF. So 3 and 4 are where we're embedding a function within itself. For GOG, that's g at x, you're going to embed g into itself. So wherever we see the variable in g, and there's 2 spots where that occurs, you're going to replace both of those with g. You're going to replace both of those x's with 5x squared plus x. So again, I'm going to square that binomial by squaring the first term. That'll give us 25x to the fourth. Multiplying the two terms together gives us 5x cubed. Doubled is positive 10x cubed. Squaring the x gives us x squared. Multiplying everything by 5. And simplifying. There's only one x cubed term here, but there are 2 x squared terms to combine. And there's an expression for GOG, G of G. For f at f, we're going to embed f into itself. F at x is equal to 2 minus 3x, and wherever we see the x, we're going to replace it with 2 minus 3x. So that one was a little simpler to do, not as much algebra, but there's the value of FOF. So you could work on those 2 questions. Right? And I should be done marking your exams today, so those marks will be in PowerSchool. They'll be done before the end of the day, hopefully even before lunch. So, and once everyone's written it, then we can go through it. Okay? So work on those questions. I'll post the solutions to Google Classroom so you can check your answers.